Okay. Okay, good morning. So we start today from what actually we have done yesterday. So I just briefly recapitulate what we have so far. So we end up of having the following operators. So we have some coordinates x mu, and so we have some momentum p mu, and they satisfy the usual commutation relations. Let me put here nu I eta mu nu. Okay. Then we have some Gauss field C and B, and they satisfy these commutation relations. Then we have some set of fermionic field psi A, psi bar B, which is delta AB, and among themselves they commute, anti-commutes, and also A and psi B is equal to 0. Then we have these fields gamma and beta, and they have the following commutation relations. So then we want to define the Hilbert space for this model. And but do you remember yesterday that also we have some charges? So instead of discussing again the charges, I just make a small table. Okay. So we have some charges for the fields x, mu, and p mu. Then the fields psi A, then the fields C and B, and the fields gamma beta. So there are one charge which is just the Gauss charge. Also, let me also put the following object: the delta of gamma and delta of beta. So this is the Dirac delta functions of gamma, Dirac delta function of beta. So gamma, I would like to remind you that gamma is a bosonic variables. Okay, so I can define the delta function, a distribution on this quantity here. So they have a Gauss number 0, Gauss number 0. They have Gauss number 0, Gauss number 0. This is a Gauss number plus 1. This is a Gauss number minus 1. This is a Gauss number plus 1. This is a Gauss number minus 1. This is Gauss number 0, and also this is Gauss number 0. Now we have the fermion charge. Fermion, and as we defined yesterday, all these fields has charge 0 respect to this charge, but the fields psi and psi bar have charge plus 1 and minus 1. And then finally there is this picture charge or picture number. Usually it's called P. And all these fields has 0, picture. There's a picture plus 1, there's a picture minus 1. Okay. So the only quantity that really carries the pictures is the delta functions of gamma, delta functions of beta. Okay. Now there is another object that I would like to also to calculate it. Is just the derivative. Let's consider the first derivative of the delta function of gamma, and then for this object I use the usual distribution laws, which is just this one. Okay, this is just the distribution equations for this function here, for this quantity, and this has okay, from a Gauss charge point of view, you see this quantity has Gauss charge 0. Okay. Now to respect this equation, so this is Gauss charge 0, as you can see from this equation here. Gauss charge is 0, fermion number is 0, but the picture number is plus 1. So this means, okay, so let's say the Gauss charge, Q of Gauss charge, this is what? This is a plus 1, and then in order to respect this equation, this must have a Gauss number minus 1, 0, and the picture, this has a picture 0. This must have picture 1 equal to picture 1. So this means this has Gauss charge minus 1, this Gauss charge 0, and picture plus 1. Now, if I for example, consider higher derivatives, for example, every time I put a derivative on the delta functions, I decrease the Gauss number. This is quite important. I will show you now why. Okay. Now let's construct the Hilbert space. For that, I need a vacuum. I will define it this way, and the vacuum is annihilated by P mu, annihilates the vacuum, beta, B, and what else? Yes, psi B annihilates the vacuum. Okay, so this is a definition of the vacuum, defined in this way. So this means the Hilbert space is generated by the other fields, namely x naught mu. Then we have a psi A. Then we have a gamma. Well, let me put the first C and gamma. And then, of course, all of them acting on the vacuum. Okay. So a generic element of the Hilbert space has the following form. So a generic element of the Hilbert space has the following form. There is a wave function here, which contains x naught mu and gamma. Then we could have powers of this psi A1, psi AP, let's say. So here we'll have indices A1, AP, acting in the vacuum. Of course, there are some of them. Of course, you have to remember that these indices are antisymmetrized, so they're going from a minimum of 0 to a maximum number of psi's. And then also there is an additional piece, which is just G. I use the same notation as I used in yesterday, A1 AP of x naught gamma and the Gauss C acting in the vacuum. So this is the most general decomposition. The most general composition expand where this F and G, I will not say anything for a moment, but they are functions in principle. They could be distributions. So they also contains not only functions of gamma, but also distribution of gamma. So it contains also a delta functions. Please notice that if I consider the Hilbert space spanned by these coordinates, by this element here, okay, you see all these fields carry Gauss number, positive Gauss number. So this has Gauss number 0, and they have a positive Gauss number, +1, okay? So there is no object here that indeed can have a negative Gauss number. But when I construct this expression here, when I construct the wave functions in this way, if this wave function f or g contains delta functions of lambda, delta function of lambda has, if it contains only delta functions, of course, I can change the picture. Well, so this could have also a picture, not only Gauss number, but also pictures. But in addition, if I consider also derivative of delta function, 1 derivative, 2 derivative, and p derivative of delta function, of course, I can put any number of derivative of delta functions. It is well defined. And then automatically I can decrease the number of the Gauss number. So in order to decrease the Gauss number, I can add the derivative of delta functions to the theory. Okay? This is quite interesting, in fact. Now, of course, one can say, well, why, for example, don't consider also other distribution like theta, the Heaviside distribution, so the step function, for example. Well, this so I'm going to consider only the compact support distributions. Okay. There are some reason from a functional point of view that shows that indeed you consider only distribution of the delta type, not of the Heaviside. So just only compact support distributions. Good. So now I want to construct two things. Okay, I want to construct two things. One thing is I want to construct. I try to construct an action, as I did yesterday. So a target space action. Okay, with all these ingredients. Okay, one more ingredient. Sorry, let me put it where I don't know. Okay, I can erase this one, this relation. Okay, I have one more ingredient, which is the following, which is the BRST charge, which is gamma psi mi p mu plus c p square minus b gamma square. Okay. Now, of course, this has, so the BRC charge has Gauss number +1, Fermi number 0, and picture 0. So if you want also to consider this charge here, okay? And as we remember, it is nilpotent. Good. Now I want to try to construct an action, okay? Yesterday, let me just remind what are the ingredients to construct an action in the case of bosonic, just only bosonic particle. So we have the integral of on the coordinates and the integral of the ghost C, okay? Then we put this, then you put the BRST charge acting this. Okay, so these guys, the BRST charge has cost number 1. Let me put just only to remind that there goes number 1, okay? And then I told you yesterday, look, there is a Berezin integral, okay? The Berezin integral on the C, this Berezin integral tells that if I have a function of the C, this is just the derivative with respect to C of the function. Okay, so it picks up from this expression here the linear term in the C. Okay, of course the C squared to 0. So then automatically you can select from this action here, from this expression here, the term in linear in C. Okay, yes. Test for target space. Target space. Now, in the present case, so we will consider some maps, x mu, p mu, and those are mapped from a line, from an interval, to some target space, okay? Now, in the case of the strings, we have worksheet fields on the target space, so here we are just a line on the war line on the target space. Okay, yeah? Right. Well, this action, it comes from the fact that we know actually the physical fields are defined by this equation. Acting psi is equal to 0, okay? And delta of psi is equal to q of eta, okay? So the physical fields are defined in this way. So they are BRST closed, okay? And they are not defined up to gauge transformation of this type. Now you see this action, and we know from these equations, from this set of equations, that indeed we reproduce the correct equation of motion, okay? Now the idea, okay, let's say this integration here is coming from a functional, let's say a path integral approach, okay? From a path integral approach, or a functional approach, if you like, it's the same, okay? A path integral approach, we know that actually we have to integrate on all the target space fields, okay? What are the target space fields? In this case, since my fields, my original fields, this and psi, at the end of the calculation, when you have a gauge fix action, they reduce it to just only 0 mode, okay? And those are the 0 mode of the original fields, okay? And the functional integration, a functional integration in usual field theory tells you that you have to integrate of the fields, okay? And now here, of the fields, we are left just only with the 0 modes. And so the fields reduce not to just a functional integral, but just a finite integral. Okay, that's the first step. The second thing is that, well, we know that this Q here, this operator here, just gives me the correct equation of motion, okay? Then automatically I can say, look, if I write down an action like this, okay, the equation of motions coming from this action are indeed the equation of motion that I want, okay? Okay, so the idea is to, I don't want to derive it, but I want just to construct it in such a way that for other models, if I have the same ingredient, I can build up an action of this type. Now I will show you. First, I will show you how to do it in this case, okay, for the superstring, let's say for the superparticle, okay. And then next week I will show you how to build a target space action in the case of bosonic strings. Really when this is not restricted just only to 0 mode, but it contains also all the Virasoro expansions of the modes, okay? So in such a way that if we need the ingredients, so how the ingredients has to match in order to build up a reasonable action, then we have a nice methods, a nice instrument to construct such an actions, okay? I don't know if it was clear, okay? Okay, so this was the ingredient how to build up the action. Okay. Now, please notice one fact, actually, that as I said before, you see, these guys implies a derivative with respect to the ghost. So this means that this quantity here, okay, that must have at least ghost number 1. It could have a ghost number 0, but at least one ghost number 1 should be there, at least a ghost number 1, in such a way that this extract a ghost number 1. Okay. Now, from, let's say, from the particle point of view, the only way to understand this procedure is that here there is a derivative. I mean, is there an integral on dc? Okay. In the case of bosonic strings, or in the case of fermionic strings, there is another ingredient which are called the anomalies. The anomalies tells you indeed what is the number of integration that you have to perform. Now here it's easy because I have to integrate only on one constant anti-commuting variable, and therefore I need that these guys must be ghost number 1. Let's see what happened in the case of a superparticle. Okay, let's do it for the superparticle. So I will have dx some power n. Then we have the integration on the psi's. Let's say psi 1, psi d over 2. Then we have the integration of dc, and then we have integration of the gamma. Again here I will put some chi, the BRST charge, and some, let me put like this chi. Right. Now you see, okay, that's okay. I will find again the integration on the coordinates. That's fine. Okay. Now there is the integration of dc. The integration of dc means that at least this object here should carry ghost number 1. Okay. This is good because already the BRST charge has ghost number 1. So this means that out of these three terms, I should pick up some terms which in total gives me ghost number 1. Fine. Now here I have, you see, here I have the integration of the psi's. Okay. The integration of the psi's, it's just again a Berezin integral because those are anti-commuting variables. So this is again a Berezin integral. So this means out of this expression here, I should take a derivative with respect to this variable. So I should take only the top form, let's say the top component in the expansion of the psi's. But here comes the problems. You see here there is the integration on these variables, the gamma. This integration of the gamma. Good. Now this is a bosonic variable, okay? So when I write down a measure of the gamma, okay, this quantity here, okay, these guys, okay, it carries a ghost number plus 1. Okay, this carries a ghost number plus 1. Because you see, the variable gamma carries ghost number plus 1. So this measure, let's say its differential, indeed carries a ghost number plus 1. Okay? That's the first thing. But then you see dc, okay, dc, okay, which is just let's say the measure for the Berezin integral. As I said yesterday, when you perform a Berezin integral, you're not doing an integral. You're doing a derivative. Okay, so this means these guys here carries a negative ghost number. So in total is -1 plus 1 gives you 0. Okay. Now here, so here there is a problem. You see, here there is a problem because I already put a BRST charge here, which has ghost number plus 1. Okay, so this means here this guy must have some ghost number, negative ghost number, in order that the total ghost number of this expression must be 0. Because this guy has ghost number 0. The total action must have ghost number 0. This has already ghost number 1. So here something happened in order to have ghost number 0. Okay, so this means here I should insert something. Let me call this something y. Okay, which is an operator which has the following property. First of all, must have a ghost number 0. Okay, ghost number 0. Now, if I want to insert something, but these somethings should not modify the equation of motion, this quantity here must be closed. And not exact. Let me show you why. Okay, so this I can cancel this definition here. Yes, I will repeat it. 1 second. This part of the measure here, which is the Gauss integrations, it contains the integration of DC. Okay, this has negative Gauss number. The gamma has a positive Gauss number. So in total, one must have Gauss number 0. Okay, so Q has already Gauss number 1. Okay, now, okay, chi, this object here, could have a positive and negative Gauss number, because we have seen if you put delta function, actually derivative of delta function, indeed I can reduce the Gauss number, even though my Hilbert space is constructed out of only variables with the positive Gauss number, Cn with psi a. Okay, so they contain only positive Gauss number, but if you consider the derivative of delta function, then I can reduce the Gauss number. So instead of taking this psi, okay, with the negative Gauss number, let me introduce, okay, just an operator, okay, just a field, psi y, in such a way that I can saturate automatically. Sorry, I made it wrong. Sorry, this has Gauss number -1. Okay, sorry. I just wrote it correct. Okay, in such a way that this Gauss number cancel the Gauss number of Q. Okay, sorry. Thank you. Good. Now, in order not to modify the equation of motion, Q, okay, on y -1 must be equal to 0. Must be equal to 0. And, more importantly, y -1 should be different of something, let's say, omega. Okay. Okay, then, okay, let's try to construct this object here. Let's try to construct this object here, okay? What is this object? Okay, let me first write down the expressions. The expression is the following, is a C, okay, times delta prime of gamma. Of course, I've discussed delta function and derivative of delta functions. Now I'm going to use it, okay? So I introduced this quantity here. This quantity here, let me put it here still in this table. Okay, this y -1, okay. Okay. Sorry, I have a problem. 1 second. No, sorry, I made a mistake here. Okay, so these guys. Okay, sorry, I made a mistake here. These guys has Gauss number -1. Okay, and so when Gauss number -1. Okay, so this guys has Gauss number -2. Okay, let me check. Let me check that. Okay. If I want to check this, okay, so sorry, I made a mistake here. I copied wrongly from my notes, okay? So if I want to check this one, I have a gamma, beta, which is part, so the Gauss charge contains a piece which is CB plus gamma beta, okay? So if I act Q phi acting on delta of gamma, okay, then I have to do the following. Huh? Sorry? we wrote minus here, okay, in this way, okay. So if I calculated this expression, here's a minus gamma beta, delta of gamma, okay. Now, you see, these guys here provides a derivative of these functions, okay. So this gives you minus gamma. So this gives you minus a derivative of delta function here. And then, okay, I use again the equation that I was writing before. So this is minus minus gives you plus gamma of delta prime of gamma. It gives you minus delta of gamma. Okay. Now, however, if you take one additional derivative, okay, I have to do again these calculations. If I do the same calculation with an additional derivative, I get that the Gauss number of this expression is this minus 2. Okay. So in this way, the total Gauss number of this expression, it is indeed, so this is Gauss number plus 1, and this is Gauss number minus 2. Okay. So finally, I have an object which has Gauss number minus 2. Okay. So Y has Gauss number minus 1, has a 0 fermion charge, and the picture number plus 1. Yep. Yeah, because okay, this expression is a gamma beta minus a beta of gamma is equal to I. Okay, so if it, well, there is an I. Okay, I don't care about the I for the moment. Okay, so if I take a derivative. So beta acting on gamma, this is just acting like a derivative, okay? If I act the charge on delta of beta, yeah, I get a plus in this case, okay? Yes, that's right. Thank you. Okay. So let me check for you that this indeed operator here, it is BRST closed. Okay. So Q on Y, the Q BRST acting on Y minus 1, this gives you, so there are two terms. One is Q of C times delta prime of gamma. And then I have minus C of Q of delta prime of gamma. Now, Q of C gives you gamma square, I think minus gamma square, of delta prime of gamma. And Q of delta, so when you act the Q of delta, this is minus 2. Then it gives you two derivatives of delta functions. And then finally, Q of gamma. Okay, but Q of gamma is 0, so this guy is 0. And then you see this one. Okay, I can use one derivative to kill one of the gammas. So I get a minus 2 gamma of delta of gamma, okay? But then I have a gamma times delta of gamma, okay? And then it gives you 0. So I always use these distribution properties of the delta functions in this way. So these guys here, this operator here, okay, has a good properties because first of all, I insert in my action here, I insert an expression which contains the delta functions, okay? Which is nice because now, okay, I don't have the problem of integrating of the gamma. You see, the gamma is a bosonic quantity, okay? Being a bosonic quantity, when I want to integrate of this gamma, okay, either I have I have a function here which is fall off in a good way, or I put the delta function in such a way that I localize the expression around gamma equal to 0. Okay. So one way to define the integration measure on the gamma, of course, this is not the only way to do it. Okay. One way that I'm just saying it is. Okay, why don't we, to integrate over gamma, okay, I will put some delta function inside, okay. This expression has the good property now, okay, but then there are quite interesting fact. Okay, let me now put all the ingredients in these expressions. So we have the following. By the way, the name of this object is called picture changing operator. Picture change operator. See, okay, I can take chi, okay, independently of delta functions. Okay, I can take chi independent of delta functions. I put the delta function here. So my expression now finally is the following. So the target space action, it is equal to integral of dx naught. Then this the integral of the, so this n, this is the integral on m over 2. Then there is the integral of dc, integral of the gamma, and then times, so we have what? We have chi. So here there is a BSD charge, gamma psi plus cp square minus b gamma square, okay, times this quantity here, which is c delta prime of gamma times chi. Good. Now, so you see that, okay, so you see from this equation a quite interesting fact. First of all, these terms here in the BSD charge is automatically killed, okay? Because you see, here there is a C and this here C. So these terms will be killed in this way. Also this term, it is killed because here there is a gamma squared and there is delta function. So there's a gamma square here and there's delta prime of this. So this is also killed, okay? So I'm left only with these terms, okay? But these terms, there is a gamma here, there's a delta prime of gamma, so I can rewrite the full expression as integral of dx naught n, integral of d psi, dc, d gamma, then we have left with chi, okay? Chi times, so here I'm left, gamma and delta prime gives you delta, so there is a minus sign, delta of gamma, then there is this c, and then I have psi dot p, acting on chi. Now, the expression chi that I was writing before are two wave functions. I can have some a1, ap on x naught gamma, okay, times the vacuum, or sorry, times psi a1, psi ap on the vacuum, plus another piece which was a c times g of a1 ap, psi a1 psi ap acting in the vacuum. Now of course this piece here drops out because there is already ghost. Here there is already ghost c, so these terms drops out, okay? These terms drops out. Now these terms, you see, here I consider just a function here, because I just consider a function of f, because I could have considered also a delta function here, okay? But already we have the correct Gauss number, because this guy has already the Gauss number correctly. So this is a Gauss number 1, this is a Gauss number -1, and this match correctly the Gauss number of this measure, okay? So the integration of the c is correct, because now there is a c here. The integration of the gamma is easy, because now I just left with the delta function here, okay? So this means out of this of the wave function here, I will only have to consider the point f1 fp for x naught times 0 acting in the vacuum. So I can remove completely the dependence of gamma here, okay? So let me conclude now. So we are left with the following. The action, it will be turns out dnx d, what was n over 2 of psi's, okay? Then I can integrate of d gamma and dc, and we are left with the chi. And the chi, I mean, chi is, we are left with what? So this is vacuum. Then there is a bunch of f, a1, ap. I consider now, well, real or complex function. For the moment, it doesn't matter, real. So this is computed gamma equal to 0 with the psi a1, psi a p. Then there is the BRST charge, but the BRST charge, I'm left only with this times p, times a function, again, another function. So it is a function a1, ap prime, psi a1, psi ap prime, okay, acting on the vacuum. See?
So when we integrate the parts, the delta prime,
Right.
the derivative act also on the x?
Sure, it could act on the side, on not on x, on gamma, on chi. You mean?
Yeah, the
Sure, it could, but then we are left with the delta functions times the gamma here. Then automatically set to 0, okay? So I'm left with this calculation here. So I'm not going to do the calculation. You can try by yourself this calculation, but you see how it works. Okay, you see this object here, it is just a psi times p, okay, acting on an expression of this type, so psi a1, psi ap, acting in the vacuum. Let's, times the function f a1 ap. This is a function of x naught times 0. Okay? Now, how can I interpret this expression? Okay, this terms has two terms. One is psi a pa times psi a pa. Okay? So this is annihilation operators, okay, which annihilates the vacuum. So psi a acting on the vacuum turns out to be 0, okay. And this is just a creation operator, okay. So this means these terms here, this is just a multiplication operator, which actually psi, it adds to an additional 1, and this p gives you derivative here. So these terms give you something. Psi a1 times psi a p, times derivative with respect to a of the function a1 ap. This is the first term. The second terms here, this psi, okay, I have to bring this psi at the end of this list. So every time I find one psi here, the psi bar produces the delta functions, okay, until I reach the 0, okay. So this means that actually this reduce in this way, delta a1 times a, so I have a psi a2 times psi. Sorry, here, can you read this from this point or not? Okay, so ap times, so here there is a derivative a of function a1 ap. Now, of course, all these indices must be antisymmetrized. So all these indices here are antisymmetrized. Also, all these indices here are antisymmetrized in this way, okay, acting on the vacuum. Good. Now the last part that I have to do the saturations, okay? The saturation, and when I've missed one thing. So when I calculated the Hermitian conjugate, here I'm missing something that I get the psi bar on the other side, the Hermitian conjugate. And so then I'm left with this annihilation operator. I have to pass this annihilation operator on the other side, okay? And then I have the structure of scalar product, okay, the scalar product. So I will have to pick up from this expression those terms which exactly matches the correct number of psi's, okay. So in the note I've done the exercise, so you can, okay, just an exercise, just set the number of a equal to 2. So in 4 dimensions, let's say 4 dimensions, the dimension mu goes to 1 to 4, 1 to 4. So the a's goes to 1 to 2, okay? So we'll have a 2 psi a, okay? And then we have 2 psi a in this way. So this means a generic field, okay, can be written as f naught of x and of course gamma times this one. And then I will have f a x naught gamma psi a times this one plus f a b, okay, of a which is also a function of x naught and gamma of psi a psi b times 0, okay. Now of course this must be antisymmetric, so then I can remove these indices here. Let me put a delta here, and these are just contracted with the epsilon ab psi a psi b in this way. Okay, so I can count. Okay, I can count how many fields I have here. I have 1 field for this one, then I have 2 fields for this 2 component, and here I get 1 component also in this case. Okay. Now you also see the following by checking the fermion charge. Okay, the fermion charge. You see the first one I have a fermion charge 0. This is a fermion charge plus 1. This is a fermion charge plus 2. Okay, so you see these guys here and these guys here is bosonic fields, component or wave functions, and this is just a fermionic wave function. Okay, and you see there is a matching. Okay, there are 2 bosonic 2 bosonic fields and 2 fermionic fields. Okay, so at the level of target space, we have the supersymmetry realized in this. Of course, this works for any dimension in this way. Now, I leave you as an exercise. In this case, for mu equal to 4, let's say a equal 1 to 2, okay, to calculate completely this expression here. This expression here is not very difficult. I mean, it's just a matter of a little bit of algebra, okay. In the note, I put the solution of this, and it's quite interesting, the result. You see, this expression here, you see this operator here, okay, there is a way to understand this operator, okay, which is rather easy. You see, this psi here, the operator, due to the commutation relations that we have established, okay, this object here, psi mu times p mu, okay, this corresponds in the target space to Dirac operator. Dirac operator. Okay. In fact, psi mu, the quantized form of this, it gives just 2 eta mu. So this is represent a Clifford algebra. The representation of p mu acting on a wave functions of x naught and gamma is just the derivative, the usual derivative of f of x naught and gamma. So this represents indeed the usual Dirac operator. Dirac operator. So this action here, okay, if you write down, is nothing else than the Dirac target space action. Okay, Dirac target space action, but it's written in a funny way. It's written in a funny way, namely, if you write down this expression, you'll see how actually all the terms come into the game. And so I just leave you an exercise how to do the calculations. Okay, so one thing I want to still to stress, okay, let me just only write down we have constructed so far. This, okay, in the case of bosonic, so we have this target space action, which is just integral of d and x naught, d n over 2 of psi, dc, so you have a chi q of 1 chi. Then for super particle, which is a super, as a SUSY on the line, so we have this bunch of psi's, then we have a dc and d gamma, and then here the expression is a little bit more complicated. We have a q of 1, then we have this picture number -1 of chi. Where this y, so here the BST charge is just only the Hamiltonian constraints. Here the BST charge here is a gamma, so there's the Dirac operator times the Hamiltonian times beta gamma square, and then there is this y -1, this is +1, which is just a c of delta prime of gamma. Now, one thing is important is the following. You see, in this case, in the case of bosonic things, when you write down a generic state, okay, we have two possibilities. One is this wave functions, and the other wave function is a c of g naught of x naught and 0. Okay, So we have only these two possibilities, okay? As I showed you yesterday, there is an interpretation. So this is just interpreted as a field, and this has an interpretation as an anti-field, okay? It's an anti-field. Okay. Now here the situation is a little more complicated, okay? Because when you construct the chi, okay, this has a function which depends on x naught and gamma, and okay, and also we have some expansion psi a1 ap, and then also there is also the other one c g. It depends on x naught and gamma, and also function a1 ap in this way. Again, the interpretation of these guys, so these are representing the fields, okay, satisfying the Dirac equation, but these are interpreted as the anti-fields of those fields. Again, so you see, every time you see something which is this expression, and then the same expression with the C in front here, it always has this interpretation. So these are the fields, and those are the anti-fields. So the situation is exactly the same. However, there is also this parameter gamma here, okay? This parameter gamma here, which also can also interpret like a replica of the same quantity. You see, gamma, okay, satisfies the gamma is equal to 0. So gamma, it is invariant under the BRC transformation, okay? So it is a BRC invariant. It carries a Gauss number +1, okay? It is a bosonic quantity. It carries a Gauss number +1. It is BRC invariant. So the funny thing is that, of course, I can filter my function with respect to the Gauss number. But indeed, this is a commuting quantity here. So this means the following, that for each power of gamma, I have a replication of the same cohomology. So in the bosonic case, I have one cohomology classes, or let's say, one cohomology classes at Gauss number 0, and one cohomology classes Gauss number 1. And there's this interpretation. This is just a field, this is just in the field. Here we still have this duplication of the cohomology. So there is this function here and this function here, of course. But in addition, we have also the possibility to expand with respect to gamma, okay? Suppose that you Taylor expand with respect to gamma here. We have for each power of gamma, we have a replication of the same cohomology, okay? We have a replication of the same cohomology. This means that the Hilbert space, the Hilbert space of physical states, somehow is replicated. For any power of gamma, we have the same Hilbert space. Okay, so in this direction there is two cohomology classes. Here in this direction there are two cohomology classes times any power of gamma. Okay, with the same cohomology. So this means the Hilbert space when you have a super Gauss, it contains an infinite degeneration, okay? And a way to fix the degeneration is given by the integration. You see, the integration, you need to integrate at least one delta of gamma. So this means the total picture of this expression must be +1. Okay, so this means the picture of this expression must be 1. So this means I pick up from this expression a given picture. I could have done it with another picture. For example, who tells me, for example, that I cannot use, for example, another picture change operator like a C of delta second of gamma? Okay, of course this is not BRC invariant, but I can try to construct the other quantity which actually has a different representation. Let's say it picks up not the gamma equal to 0, but for example the first power of gamma, for example. Okay, so this means I can try to define my action. I can define my quantity at a different level. Or let's say, the integration tells me that since I have to integrate of the gamma here, I need at least one delta function in order to select correctly my pictures. Okay? This is very important because in the case of string theory, okay, let me show you the following. In the case of string theory, this is, okay, this action, the target space action, in the case of string theory, becomes just an integration of this one. Now here there is integration of 3 Gauss, C1, this C0, this C -1, okay? This is the integration of 3 Gauss. And then there is a states, then there is a BSD charge, and then there is the states. Okay, so here there are 3 buried in the integral that I have to perform. Okay, this is just only for the 0 mode. Of course, one has to do also non-zero mode, but the 0 modes require this integration here. Okay, so this means out of this expression, I have to extract ghost number 3. Okay, so the QBRST already carry ghost number 1, but I have to extract from the states quantity which has ghost number 3. Okay, okay. So this is the celebrated Witten string field theory action. String field theory action. Okay, the Witten string field theory action, and which has the form of a Chern-Simon type of action. So there are 2 fields and the BRST differential. Okay, BRST differential. And the fact is, as I said, here there are 3. Here there is 1 ghost. So the states here they have ghost number 0. Okay. Now here I have 3 ghosts. So the states here must have ghost number 1. Of course, I could have also ghost number 0 and ghost number 2. And also I can have ghost number -1 and ghost number 3. Okay, there is a full expansion in the case of string field theory. Okay. Now what happened for this is for the bosonic. So okay. What happened for the fermionic things? So the target space. So this is for the bosons. This is for the fermionic things. Okay. So I will have dn x naught, some bunch of deep size. Okay, then I will have 3 of this ghost, C1, DC naught, DC -1, okay? But then I have 2 bosonic ghosts, gamma half and D of gamma -1/2. Next week I will show you exactly where are these gamma half and gamma -1/2. But then here I have chi, Q, okay, and then chi, okay? So this guy has ghost number 1. Good. The states here, chi must have ghost number 1. Okay. But here you see there are 2 gammas to integrate over. So then this means I have to add some other picture change operator in order to soak up also the gamma integration. So here will be a picture change operator which has a picture number +2. Okay, and the ghost number of these guys, I don't remember now, I think it is 0. In this case, it's 0. Okay? So this form of this action, the form of this action, is one of the form of the superstring field theory actions. Okay, but what is very important is the presence of these guys here, this picture change operator, in order to saturate the correct ghost number here. Okay, so let's say given these ingredients, then next week I will show you how. Okay, what are the ingredients in the case of string theory? Okay, so what are the ingredients to define this action here in the case of string theory? And so then we will see actually how going from the particles to the strings actually the things changes in this way. Okay, I hope that I give you. Okay, let's say this construction here. Okay, the construction of this action here is still under studies. I mean, nobody know. I mean, in this case, for example, it is easy. It is rather easy. Let's say not easy, but it is rather easy to construct the interaction. Okay, and actually there is one additional terms, and that provides the full interaction of open string field theory, which is a beautiful theory. Okay, in this case, okay, you see this is just the kinetic term, so it gives you the equation of motion, the free equation of motion, but the interaction terms are not known so far. So of course there are some ideas. There are several versions. For example, you can take this y here. You can distribute this y on the field chi. So instead of taking a wave function which depends on gamma, you take delta functions and so on. So there are several versions. I hope that I gave you some ingredients, okay, in order to, I mean, at least if you read the papers on this subject, you understand what is going on, why you need those ingredients and how to deal with them, okay. Let's Let me see if I want to say something more. Let's say this is the boundary of the research today. Okay, so recently, even 2 days ago, there was a beautiful paper trying to construct such an actions. And let me tell you one fact. Okay, now if this is just the string field theory actions, the string field theory action, so the target space action. In this case, we have seen that this action produced the Klein-Gordon equation of motion. Okay, so the target space action produced exactly what you expect the Klein-Gordon equation of motion for the scalar fields. That gives you the Dirac equations in the target space. So again, so we started from let's say from a fermionic particle or superparticle, and that's produced a Dirac equation. Good. If you try to construct this action from this, you get what? You get all the possible equation of motion. There is an infinite number of fields, and you get the correct equation of motion for the fields. So you have a Maxwell equation of motion for the massless fields, then you have a spin 2 massive states, spin 3 massive states. The full list, the full tower of states that you generate from this are correctly reproduced as the equation of motion from this action here. And plus interaction, it's a beautiful theory. Now, what concerns this one? Okay, that should give you at least the kinetic terms of supergravity. Okay, the kinetic terms of supergravity. Which kind of supergravity? Well, this is in 10 dimensions. Okay, in 10 dimensions supergravity. Okay, 10-dimensional supergravity. You know there are two versions of this. There is the type 2A and the type 2B. Okay, supergravity, and the difference between the two supergravity is just the type of Ramon-Ramon fields that you have in the theory. Okay, now for what concerns type 2A, there is a target space action. There is an action for type 2A supergravity, okay, target space supergravity. There is a good action, I mean, whose equation of motion are really the correct supergravity equation of motion. For what concerns type 2B, there is not an action, okay? There is not an action, and the reason is the following. You know that in type 2B there is this Ramon-Ramon potential, which is a C4, okay, which is a 4-form gauge potential, and its field strength is a 5-form, okay, its field strength is a 5-form, but in type 2B, in order to have the correct matching between bosonic fermionic degrees of freedom, this must be self-dual 5-form, okay, so the 5-form is a self-dual. However, for self-dual theories like this one, 5-form, there are in 6 dimensions, in 4 dimensions, in 2 dimensions, there are all examples of these types. There is no way to write down an action, even at the free level, which implement this equation as an equation of motion. Of course, one can say, well, why don't add this equation as an equation of motion just by adding a Lagrange multiplier? If you try to do it, so you just put a Lagrange multiplier that implement as an equation of motion the self-duality condition, you immediately see that the Lagrange multiplier starts to propagate as a physical degrees of freedom. So even though you add this condition, there is something which is just a new field which is started propagating. So the balancing between the degrees of freedom is spoiled by this equation. Of course, you can add another equation of motion to cancel these new degrees of freedom, but then this goes over and over. So you never reach a point because you always divide by 2. So you add this means that you have to halve the number of degrees of freedom. This is a self-duality condition, halves the degrees of freedom of the C4 potentials. So this means then if you add this condition to the action, okay, so you're propagating the full set of fields plus Lagrange multiplier, which effectively cancel the degrees of freedom. However, of the Lagrange multiplier propagates the full degrees of freedom, so you need to cancel them, and this goes by 2 halves. So you add the halves, you remove halves, then you add halves and remove halves, okay, and so on. And well, there are several ways. If you like, I can tell you the story, but it's rather okay. So this means that this action at the target space action should reproduce the supergravity action type 2B. However, at the moment, nobody knows indeed if this actually produces the correct supergravity action. So it's a matter of research. This is quite important. As I said 2 days ago, there was a nice, beautiful paper by Ashok Sen trying to argue how to construct such an action which actually reproduce the correct supergravity type 2B in 10 dimensions. Okay. Now I want to do the following. Okay. Yes. That's right. Okay, as I say, as far as I know it, okay, there are at least, I think, 4 attempts to do it, okay? One attempt is in a non-covariant way. Okay, then you spoiled the Lorentz symmetry for the beginning, okay? There is another attempt using an infinite number of fields, okay? But then you know if these things converges, okay? There is another attempt using, kind of harmonic superspace, so you have, again, an infinite number of fields, okay? And then you try to construct the action, at the end, the action doesn't reproduce things. Now, actually, there is this paper by Ashoksen that they say, okay, even though if you try to do it, okay, you run into the problem. So, nobody knows the solution for the moment, yes. That's right. Right, but then, okay, in the 11th dimension, okay, if you like, I can show you, but in the 11 dimensions, okay, in the 11 dimension, there is another action, okay, which is a beautiful action, which is a target space action, again, which contains dn of x naught, well, 11, okay. Then there are some other fields, theta, and there are 32 thetas, which are anti-commuting variables. And then there are new objects, lambdas, which are bosonic ghosts. And then again, there is chi, some BRST operator of chi, okay? And there is a target space action which reproduces the supergravity, at least the kinetic part, so the free action, okay? Again, of the same form, okay? And, but this ghost here, there is a bunch of them, okay? There's a bunch of them. Actually, I think 23 of these guys. 23. Yeah, I think it's 23. And this have some special properties that, if you like, I can tell you, okay? So there is a version in order to do it also, let's say, on the same line, on the same footing, to reproduce an action of this type. But let me do it one other step. So the rest of the lecture, I want to do another example. So next week we'll directly go to strings, so adding modes, okay? But today I want to do one more example, still sticking to just only 0 modes. Okay, we remember the starting point of the bosonic. So I'm back to the origin. But now I want to do something else. Now I want to do, so yesterday we did a supersymmetrization SUSY on the line. And we did the following. The variation of psi mu was equal to epsilon psi mu, and the variation of psi mu is equal to minus or plus, remember, p mu, in this way. So we add to the action the new field psi mu, okay? And you see, this field has the following properties. So this has a bosonic field, this is a fermionic field, so, but the index here is a vector index, okay? So it's the same type of index. So it's the vector representation of the Lorentz group. Good. Now I want to do something different. Okay, I want to do SUSY, supersymmetry, but in the target space. So instead of adding, I knew the new fields, which is this one. So this is a boson. Okay, this is a fermion. However, the index here, so if this is a vector representation of Lorentz group, this is just a spinorial representation of the Lorentz group. So alpha now is a spinor index in the representation. So here are the same representation. So if I perform a Lorentz transformation, okay, mu acting on this, it just rotates in this way. So this is just the Lorentz transformation of these fields, okay. In this case, if I perform a Lorentz transformation on these fields, okay, the transformation on this one will be just L mu nu, gamma mu nu, alpha beta, theta beta. Let me put it up and down here in this way. Okay, so this is just the induced spinorial representation on the spinor fields. Okay, so this is a vector boson and fermion, and this is a boson, a fermion, but this one has an index alpha in the spinorial representation. Let me give you just a few details about the spinorial representation. I will stick. I mean, you can do several exercises, okay, but I will stick to in 10 dimensions because we don't have time to do other cases in 10 dimensions. So the index mu goes from 0 to 9, okay, so I consider the Lorentz group SO9. I can do also Euclidean, okay. Yeah, let me do it Euclidean, it's even better. 1 to 10, so SO10. And alpha, the index alpha, okay, I take it 1 to 16, okay. So I'm considering, so these are the vector representation, x mu, okay. And for theta, I use Majorana-Weil representation in 10 dimensions. That is the smallest irreducible representation, smallest spinorial irreducible representation in 10 dimensions, which is a Majorana-Weil fields. Okay, so this index alpha goes to 1 to 16, and those are real anti-commuting variables. Okay, so in this case, the gamma matrices. I will define in this way, gamma mu, okay, and it have two indices, alpha, beta, or there are gamma matrices which has upper indices. So say the original gamma matrices mu, gamma, it is written like 0, gamma mu, alpha, beta, gamma mu, alpha, beta. So essentially those things are the Pauli matrices in 10 dimensions. For the Majorana-Weil representation, I can choose this Pauli matrices here. They have the following property. The Clifford algebra representation is this one: gamma alpha beta, gamma nu beta gamma, plus gamma mu, sorry, gamma nu alpha beta times gamma mu beta gamma is equal to 2 eta mu nu delta alpha gamma. Okay. The Clifford algebra is represented in this way. So the numerical value of these matrices are the same. Okay. So if you take alpha 0, 1, 1, it's the same numerical value of gamma alpha 1, 1. So the numerical value are the same, but the indices are down or up. Okay. And there is no invariant tensor which allows me in 10 dimensions to raise a lower one of these indices. So I cannot contract these indices by using a lower let's say, charge conjugation matrices. Okay, so I only have a chronicle delta this way. Okay, with this index in this way. So I have no way to raise and lower indices. Okay, right. So there is also an identity which is called a Firth identity in this case, which is the following: alpha, so gamma alpha beta, gamma mu, gamma delta. So if you cyclic permute 3 of these indices, this gives you 0. So this is the Firth identities between gamma matrices. Firth identities. If I consider a bispinor A alpha beta, so this is bispinor with both lower indices, okay, I have the following decomposition. I can have a vector, gamma mu alpha beta, then I have 3 forms, gamma mu nu rho, so it's unsymmetric gamma mu nu rho alpha beta, and then I have a self-dual 5 form, self-dual mu nu rho sigma tau, gamma mu nu rho sigma alpha beta. Okay. Okay, so this is self-dual 5 form gamma matrices. Okay, so let's say this is just a bispinors. Okay, so it's 16 square, and this is decomposed into a vector. Sorry, this is a 3 form, and this is a self-dual 5 form in this way. If I consider, however, another bispinors where one index is up, down, and one index is down, it is decomposed into a scalar, delta alpha beta, in a 2 form, mu nu, gamma mu nu, alpha beta, and into a 4 form, gamma mu nu, rho sigma, gamma mu nu, rho sigma, alpha beta. Again, this has a 16 square component, and you decompose in terms of this component here. You can easily do the calculation, try to see if indeed actually has the correct decompositions. There is a bunch of identities and relations. For example, if you take this gamma matrix, you calculate the gamma mu 1, mu p, gamma mu. Yes? Right, in 10 dimension there is no, I mean, if you use this notation here in the Majorana-Weyl representation, the index up and, you cannot raise and lower the indices. You can only contract it. You see, the gamma matrix is gamma mu as an index alpha beta. So this quantity here, which is gamma mu is defined in this way. It is gamma mu alpha rho, gamma nu rho beta, and then you have to antisymmetrize this. So it's gamma nu alpha rho, gamma mu rho beta, and divide by half. Okay, so you built up this. Sorry, I forgot to say that these are the antisymmetrization, the product of gamma matrices antisymmetrizing those indices. Okay. So there's this property here, which is 10 minus 2 to the p, where p is just the number of indices here, times gamma 1 nu p, okay? Which is actually quite important relation. If p is equal to 5, this gives you 0. So the contraction gamma mu, gamma 5 with 5 indices, gamma mu is equal to 0. That is quite important in some derivation. Okay. So you see, this is just the way how the Lorentz generator is acting on the spinor theta. Okay. So this matrix here, which is the Dirac matrix, which produces the rotation in the spinorial representation. Okay. I put in the note all this derivation, but actually, if you want to find a good reference, it is a chapter 5 in the Green-Schwarz-Witten book. In Green-Schwarz-Witten book, there is the chapter 5 which contains all these details. Now, okay, so here the supersymmetry is written in this way. So we have add a field psi to the field x, and the supersymmetry parameter, this is epsilon, is the SUSY parameter, which is just a which is a Grassmann parameter, and it carries no index here. Okay, actually it is a worldsheet supersymmetry. However, here the supersymmetry is different. Okay, then is a target space supersymmetry. Okay, target space supersymmetry means what? Well, means that this coordinate here, x and theta, can be actually understood as a superspace coordinate. So these are superspace coordinates. So these are the bosonic coordinates, and these are the supersymmetric coordinates, so the superspace coordinates, okay? And then when you perform a supersymmetry transformation in the superspace, okay, a supersymmetry transformation in the superspace correspond to what? Corresponding to translations along the super coordinates. So translation means d epsilon goes into some parameter epsilon alpha. So again, this quantity is anti-commuting variables, but you see it carries an index in the spinorial representation. So this is just a supersymmetry transformation. It's a SUSY transformations of the coordinate theta. What about the axis? Well, if this is just a supersymmetry, that is just minus. I define it in this way. Of course, you can change the sign, and consistently you can do the game. So epsilon, alpha, gamma mu, alpha beta, theta beta, divided by 2. Okay, it resembles this one, because you see the supersymmetry transformation of x goes into epsilon times psi. Here just epsilon times theta, but in the between there is the gamma matrix here. Okay. Then, of course, you can check that this is indeed, again, a supersymmetry transformations. There is a big difference. So this is a linear transformation, so it's a supersymmetry transformation which is linear. This is a non-linear transformation of supersymmetry. So it seems to be linear because you see in this is a linear because x goes into theta, but this is non-linear transformation. Okay? Yeah, you can interpret this as a Goldstino breaking type of supersymmetry, but okay, I don't want to enter in these things. Okay, so this is supersymmetry. Okay, in this case. Good. Well, now, okay, so then I have to do something with my action. I have to do something with my action in order to make it supersymmetry invariant under such supersymmetry transformations. Now, if let's consider now, I have to make a supersymmetry transformation of this expression here, okay? So, and let's consider also derivative x mu with respect to d tau, okay? Now, if I make a supersymmetry transformation of this quantity here, let me put an epsilon here just to remind this is supersymmetry here. If I make a transformation of this type, let's make a transformation, so a derivative of d tau. So I get a minus epsilon gamma mu of theta divided by 2. And this gives you what? Well, this gives you minus epsilon gamma mu of d theta tau divided by 2. Now, look, I pull out epsilon out of the derivative because now here I'm taking epsilon constant. Epsilon mu is constant. I'm not going to promote to a local parameter, so I'm not going to do a supersymmetry transformation, local supersymmetry transformations in the target space. Here, epsilon I promoted to a local parameter, so epsilon becomes a function of tau, and then I derived the super, let's say, local supersymmetry transformation for the action here. Here, I'm not going to do it, so epsilon will be still remain a constant parameter. Okay. Now, you see that I can cancel these terms, by adding to these variables, to this expression, I can cancel these terms by adding something like a half theta alpha, gamma alpha, d of theta beta d tau. Let's perform a supersymmetry transformation of this expression here. If I perform a supersymmetry transformation, this gives you exactly what I got before, over 2 gamma mu of d theta of d tau. Okay, but these terms, you see epsilon, theta transform as an epsilon, so I get half of epsilon gamma mu d theta of d tau. And then I should transform also theta here. But you see, theta here appears under derivative, epsilon is a constant, gives no contribution. So these terms cancel out. Okay, so this quantity here, it is indeed in supersymmetric invariant. Let me call it pi. So x mu plus half of theta gamma mu of theta. So if I want to, also cannot put indices like this. Okay, so this means my action, okay, becomes a supersymmetric action if I do the following. I have d tau. I replace these guys by my p mu plus half of epsilon p square. So in order to make it supersymmetric invariant, what I have to do? Well, I have to just only to say what are the supersymmetry transformation of p and e. And the supersymmetry transformation E is equal to 0, and the supersymmetry transformation of P is equal to 0. And the action it is now supersymmetric invariant. Is invariant under supersymmetry. Okay, good. Now we look at this action here, okay? Let me write down explicitly, okay? Let me write it down in explicit way. Now here I can write in this way, theta, alpha. Here there is a gamma, so there is a p mu, gamma mu, alpha beta, theta beta, okay? And then there is a plus half of EP square. Okay. Now you see the following. Okay. You see the following. This expression, these terms here. Okay. It looks like as kinetic terms for the theta. Just let me write down for you in order to compare what I've done yesterday. So yesterday we got these terms. So there was minus half of a psi mu dot. This one terms, and then there is an additional terms which is chi psi mu p mu. So those are the terms in the action of yesterday. Okay, so okay, these terms here we find it good. This is nice. This is also the Hamiltonian constraint, if you want to call it. Now here there is the kinetic terms of the fermions. Okay, and here there is the coupling between the Dirac constraints, or if you like. The coupling with the gravitino. Okay, so these guys here are the coupling with the graviton and gravitino, with the, let's say, supergravity multiplet, and these are the kinetic terms for axis and for psi. Now here the situation is rather similar. So we have the kinetic terms for this one. We have the Hamiltonian constraints, okay, for the gravitino, okay, on the line, okay. But here there is this nice term, these are funny terms. You see, okay, it resembles a little bit these Dirac terms, okay, because there is a theta and theta dot. However, there is in the between p, okay. So indeed, this is in interaction terms. Interaction term. More than kinetic terms, actually. Okay. First. Second, of course, there is no gravitino couplings because we don't have a supergravity multiplet on the line. Okay, we just only have the Einbein, which is just the graviton on the line. Okay. However, there is a problem. Okay, and the problem is the following. You see, in this framework, okay, there is a matching between the fermionic and bosonic quantity. If I have n bosonic quantity, I will have also n fermionic quantity. I've shown this morning earlier, I've shown you that when you write down the physical fields and you construct the wave function, there is always this match between bosonic and fermionic components. So the supersymmetry in this case is preserved steps by steps. Okay. However, here the supersymmetry is preserved, but the matching between bosonic and fermionic degrees of freedom is already spoiled, because in 10 dimensions this has a 10 component, but this has a 16 component. So there are 10 bosonic fields and 16 bosonic fields. Okay, so the matching is already spoiled at this point. So the action is supersymmetric invariant, but there is no matching between the bosonic and fermionic degrees of freedom. So this means there should happen something in order to have the matching. Okay, this is the first things. The second things I want to tell you another fact. Do you remember that yesterday we have analyzed this action here, and when I analyzed this action here, it turns out, well, we have seen also this morning, that indeed two constraint emerges. One constraint is a p square is equal to 0, and the other constraint was a psi mu p mu is equal to 0. Good. Now these two constraints appear in the BRST charge, QBRST, okay, coupled to Gauss fields, psi dot p plus a CP square minus b gamma square, okay. So for each constraints, okay, there is a couple of Gauss fields, okay. There's a couple of Gauss C and B, and there's a couple of Gauss of gamma and beta, okay. Well, what is the role of these Gauss fields? Okay, what is the role of these Gauss fields? As I said really at the beginning, okay, the Gauss fields, okay, are introduced in such a way that they effectively cancel out the unphysical degrees of freedom related to x and p or to psi's. Okay, why? Well, do you remember actually when we write down the commutation relations? At the end, when you quantize the theory, we find out this commutation relation, P mu equal to I eta mu nu, and the commutation relation of psi mu equal to 2 times eta mu nu. If you consider the Lorentz signature, okay, what happened? That here there is either +1 and minus, or in this also case there is 1 + 1 and the other minus. Okay, so the fact that there is a set of diagonal terms which has a plus sign, a set of things which has a minus sign, this means that if you construct the norm of the Hilbert space constructed out of those operators, it turns out that the Hilbert space contains negative norm states. Okay, so this means that this is not really in Hilbert space. So the scalar product is not positive definite. Okay, so this means that you have to cancel some degrees of freedoms, the unphysical degrees of freedom, in order to have a positive definite scalar product in your Hilbert space. And indeed, the ghost CMB are effectively works in such a way that you cancel unphysical freedom. Or, say in different way, the Hamiltonian constraint p squared equal to 0 is such a constraint that allows you to define a Hilbert space which has a physical interpretation, namely positive definite scalar product. In the same way, gamma and beta are effectively cancel 2 degrees of freedom coming from the fermions. Now, the fermions are fermionic fields, and then I need the super gauss with opposite statistic in order to cancel those degrees of freedom. If you remember, for example, what happened in Yang-Mills theory. In Yang-Mills theory, you have a gauge bosons, which has 4 degrees of freedom, and then you add the 2 gauss, one gauss, the anti-gauss, which effectively, in all the loops, in all calculation, cancel exactly against the longitudinal and the time direction, and time component of the gauge field, in such a way that the polarization at the end is always 2 polarization for each color of the gauge boson. Okay. Now here, so this means counting degrees of freedom, so this CMB count negatively, which removes 2 degrees of freedom. So the counting of degrees of freedom is if the dimension of the space is D, okay, because of BC, the dimension is D minus 2. So these are D minus 2 independent degrees of freedom, which are physical positive definite norm. This is for the X's and P. And what about the psi's? Also, because of this super ghost, this is reduced to D minus 2, okay? So the supersymmetry it is preserved in each steps, because when you quantize it, you introduce the Gauss field, you never break any Lorentz symmetry, the quantization is completely covariant, but effectively, the degrees of freedom that you are left with are exactly D minus 2 and D minus 2, and the matching is performed at the classical level and the quantum level once you have quantized the theory. Yes? Yeah, let me come to this point. Okay, it looks like a kinetic terms. Let's say, suppose that the p assume a given value. Okay, this looks like a kinetic terms. Okay, but it is not really kinetic term because it is also an interaction term. And then I will show you how to get the kinetic terms out of this action here. But this discussion is very important, and namely how the constraints effectively works in order to reduce from the classical fields to physical fields. Okay. Now, here the symmetry is spoiled from the beginning. First of all, this action here has invariant under diffeomorphisms. Okay, you can see in 2 ways. Either you perform a local diffeomorphism reparameterization on the line, okay, and then you find out that this action is invariant. As we have done yesterday and the day before, you can perform local transformations of the graviton in such a way that is invariant. The other way to say is, look, if I consider the equation motion for E, the equation motion for E gives you again the Hamiltonian constraints. So the Hamiltonian constraints will be related to some ghost CMB, and again this ghost here reduced effectively to D minus 2 to the physical degrees of freedom for X and P. So the degrees of the degrees of freedom for X and P are effectively reduced to D minus 2. But what about the theta? What about theta? I have 16 of them. Okay, and so the matching of degrees of freedom is not working here, and even worse, it doesn't work even here. Okay. However, this action here has a beautiful, yes. has a beautiful symmetry, okay? There is a new gauge symmetry, which is called kappa symmetry. Which is a new gauge symmetry, which allows me to remove half of them, half of the thetas, okay? And remove half of the thetas allows me to having the matching. Let me show you how it works, okay? Gosh. Here. Okay, let me show you how it works. Let's consider this action here, okay? And let's derive the equation of motion. Let's derive the equation of motion, okay? Okay, what are the equation of motion in this case? Well, one equation of motion, if I take a derivative with respect to p, okay, I get x mu plus half of theta gamma mu theta dot, okay, plus here I get e p mu equal to 0. That's the first equation of motion. Then I can derive the equation of motion for theta. Okay, here again it works like in the case of yesterday. Namely, if I take a derivative with respect to theta, I can take a derivative here, but I can also take a derivative here. But once I take a derivative here, I can have, have a partial integrations. Okay, when I do partial integration, I have a derivative of theta, which will reproduce again the same expression, but also I have derivative on p mu. But let's consider first the derivative with respect to x. If I take a derivative, the equation of motion for x's, I get the p dot mu is equal to 0. Now I take a equation of motion with respect to the theta. So equation of motion for theta turns out to be p slash dot is equal to 0. So this is okay. Let me put it in explicit form. Alpha beta derivative with respect to theta beta respect to d tau is equal to 0. And then finally I have the Hamiltonian constraint p square is equal to 0. So these are the equation of motions in this case. So these are equation of motion in this case. In the notes I put some rather detailed derivation here. Okay. So so here to derive this equation of motion, I use the p dot is equal to 0. So I don't get exactly such an equation of motion, but I get a combination of equation of motion using this one. Okay. Good. Now let's also compute the conjugate momenta. Okay. So the conjugate momenta of axis, it's easy. Conjugate momenta is what? As usual, when I calculate the conjugate momenta, let me call it the small p. I don't know how to call it. Small p. Okay. It's just a derivative respect to the Lagrange respect to x dot mu. Okay, so the conjugate moment of axis is just p, as we expected. Okay, but the conjugate moment pi alpha of derivative Lagrange with respect to theta dot alpha, which has an index down. Okay, the conjugate moment of this one, it is what? Well, if you calculate here, I get something which is a p slash theta. P slash theta. Okay, so this means the following. If I define d alpha as a pi alpha minus pi slash theta, okay, d alpha is a pi slash, then, okay, the fact that the d alpha is 0, okay, it is a new constraint. a new constraints. So I have two constraints. One is the p squared is equal to 0, and the other constraint is d alpha is equal to 0, where pi is just the conjugate moment of theta. Usually the people write down the equation for the constraint in this way. So the equation of constraints is written in this way. So that means that on the space you impose this constraint. So these are the dynamical equations, and these are the two constraints equal to 0. However, let's compute. Yeah, I mean, this is just a definition, okay? This is the constraints. You say p alpha is equal to p slash theta. I just recovered that. And you see, this quantity here, it doesn't depend on derivative, okay? So I can read this equation as a constraint. So pi alpha is equal to p slash theta. This is just the constraints, okay? Okay, that's a very simple thing. However, let's compute the Poisson bracket, okay, between the d alpha and d beta. So this is just the classical Poisson bracket, okay, the classical Poisson bracket, okay, p alpha and d beta. Now, and for computing such a Poisson bracket, I use the fact that pi alpha, which is the momentum, and theta beta in the Poisson bracket gives you delta alpha beta. That's the usual definition of Poisson bracket. So this pi alpha is the conjugate moment of theta, okay, and in the Poisson bracket, by definition, it gives you this one. So if I compute the Poisson bracket between d alpha and d beta, what I get? Well, let me write down. So it's pi alpha minus pi slash theta alpha, comma, pi beta minus pi slash theta beta. And this gives you what? Well, you see, pi alpha could act here, okay? So this means pi alpha and theta gives you minus p slash alpha beta. Okay, and this gives you another minus pi slash alpha beta. So the total answer is slash 2 pi slash alpha beta. Okay, so the Poisson bracket between d alpha and d beta is equal to minus 2 p slash alpha beta. So these equations, it's rather a little bit embarrassing because it tells me the following, okay? First of all, if you remember the first lecture, I was saying the following. Suppose that I have a set of constraints, Fij, okay? And there are several situations. Either they commute, or they form an algebra, or there is a new operator here, phi prime, and then I have to add this to the sector, or it closes to some other operators. Okay, another operator, let me put delta ij, okay, an operator here. Now, of course, if I generate a new operator here, this could be a C number, for example, okay. If I have these new generators, what I do? Well, I can take this generator here, put in the same set of generators, and then calculate again the algebra here. Then I say, look, if this is my constraints, if the alpha is my constraints, okay, then if I compute the commutation relation, the Poisson bracket between them, I produce this object here. Then I say, okay, why don't take these constraints, p alpha equal to 0 as a constraints? Okay, but p alpha equals to 0 means what? Well, it means p mu is equal to 0, okay? But p mu is equal to 0, so this means that my particle is just at rest, so the p is equal to 0, so it doesn't move, okay? So the moment, so these constraints here, it's two strong constraints, okay? So this means that these constraints that I've chosen here is two strong constraints. Let me make it a little bit weaker, okay? Okay. So this is the situation where actually I have the possibility to introduce these constraints in the set of the constraints, but if I'm going to do it, my particle will stop, okay? So it doesn't move at all, Okay, so let me try to make these constraints a little bit weaker. Okay, and then I construct the following constraints. I take the projection of p slash of d. So this means gamma mu alpha beta d beta on p mu is equal to 0. So this is just my new constraints. Let's see if this works. Okay, let's see if these constraints it is a little better. Let's compute now what is the p slash d alpha times p slash d beta. If I do the calculation, you can do it by yourself, you get something which is 2p square p slash alpha beta. Okay, then you see that this is just a minus p slash alpha beta. Let me put this in front of this. Now you see these two constraints. Okay, this is two constraints. This is the closest. Okay, it is not a Lie algebra because it depends on the momentum p. Okay, but it closes again on the constraints. Okay, so this is an example where this is not really a Lie algebra. Okay, because it is an algebra, but it's not a Lie algebra because these are functions. So these are structure functions, not a structure constant. But the Poisson bracket, these two constraints, closes on the constraints. And this is the constraints of the theory. We already find these Hamiltonian constraints of the theory. Okay. So good. So I found out that there is such a constraint. Okay, that I can impose such a constraint on a theory. Okay, and which is a weaker, let's say, a weaker version of this one. This constraint was too strong. Okay, this is too strong constraints. Yeah.
Why did you choose this, or how were you led to this?
Oh, how? Okay. You see. No, the reason is the following. If you look at this object here, p slash alpha, okay, and you calculate the matrix. I mean, this is of course a 16 by 16 matrices, okay. You find out that the rank of this matrix is just 16. So this means the matrix is invertible. Just take the trace, and then you imagine to see that this constraint implies these constraints, okay. I want to make this constraint a little bit weaker, okay. And then actually the way to do it, okay, is projected on some p slash. Okay, so projecting on the p slash allows me to separate. Okay, the point is this object d alpha, okay, contains two types of constraints. It contains first class constraints, plus second class constraints. It contains first class and second class constraints. This d alpha. Okay. However, if I want to separate between the first class and second class, I have to break Lorentz invariance. Okay. There is no covariant way to break. I mean, the things that I want to do. I want to have a Lie algebra. Okay. Sorry, I want to have an algebra. Okay. In order to have an algebra, I need the first class constraints because the second class constraints do not form an algebra. Okay. So, but if I want to separate between first class and second class, okay, I have to project in such a way that. But there is no covariant way to do it. Okay. I cannot really separate between them. Okay. The only things I can do is just projecting these constraints with the p slash. Okay. In such a way that I somehow selects, or let's say I just select so I'm projecting out of the alpha just only the first class constraints. Okay. So the way to weaken is okay, if I try to impose both constraints on my states, it's too strong. Okay, and the way to do is just projecting out at least the second class constraints. Yes. Yeah, you see, this guys here. Okay, you can separate between. Let me try to see if actually I have a. Well, essentially, Essentially, you can do the following. Essentially, you can do the following. D alpha, you can write like 1 minus p slash of d alpha plus p slash of d, okay, in this way. Okay, that's of course I can do it. Okay, I can always do it, and okay, in such a way that yeah. So I separated this p slash d and this one. Of course, if I want to make this as a projector, I certainly have to do something. Okay, let me calculate this one. Okay, this gives you 1 minus p slash times 1 minus p slash. This gives you 1 minus 2 p. Okay, so there is an alpha here, alpha. So 2 alpha p slash, and then plus alpha square p slash square, but p slash square it is gamma mu p mu, gamma nu p nu. Okay, this gives you p square. Okay, so this means this gives you 1 plus alpha square p slash p square, and then I have a minus 2 alpha p slash. Okay, so in order to reproduce, okay, this must be equal to 1 minus alpha p slash. Okay, so this means what? This means that yeah, I have to do something more. I have to divide by 2, so I get by 4. This is divided by 4. That gets divided by 4 in this way. So this means that alpha square, alpha can take like 1 of square root of p square. Okay, if I do that, okay, so let me write down this way. So it's square root of p square. So also the square root of p square divided by 2. So this is just a projection operator. So I project out, okay, so this is a projection operator. So I project out, I separated in this part, such a way that this is a projection operator, okay. And so then I separate between this, okay. However, you see that I have to divide by this twice here, square root of p square, okay. So it is a no local operation that I'm doing, okay. Yeah? Yeah, but here I'm not considering, okay, this just to say that I can separate the d slash in this way, okay. In order to do this separation, I need to have a square root of p square, okay. But I will not do it, because if I want to do it, I run into problem, because when p square becomes 0, okay, then I run into the problem. So I will not do it in this way. So just only to say that I can project out the d, the first class and the second class constraints in this way, okay. However, to do it that, I have to divide by square root of p square. So I will not do it that. I just only to construct this p slash d, and then find out that the p slash d form a first class constraint set of algebra. Okay? Okay, let's now see what happened. Okay, so the constraints are now the following.
So are you happy with this computation?
This one, yes, I'm happy with that. Because these constraints close again on these constraints and do not force me to take p slash equal to 0, but p squared is equal to 0. Okay. But let's see if this works. Okay, let's see if this works. Okay, so my constraints now is p slash d is equal to 0. Okay, let's see actually what is the. Let's try to see what are these constraints, what happened to these constraints when these constraints acting on some fields, okay? Let me do it in the following way. First, I take these constraints and multiply by a parameter which I'm going to call kappa. Yes?
Does it mean that we have changed the definition of the moment associated
To the particle, to the theta, yes. Essentially, yeah, I somehow say, look, the momenta is defined in this way, but this is too strong constraints. So I just multiply it by slash, so I projected, I just consider a part of the momentum, not the full momenta, essentially. I projected momenta for the thetas. Let me consider now the following, okay? Take the constraints and multiply it by the kappa, by a new field, kappa. So kappa is a field which depends on tau, on the parameter t, And there's a spinor index, which is just, you see, this is just kappa alpha, gamma mu, alpha beta, p mu, d beta. Writing this way. Okay, I just take the constraints and multiply by a quantity in such a way that this is now becomes a scalar quantity. Then I calculated the Poisson bracket. Now, if I want to say, for example, what is the action of the given constraints on a field, on the field theta, for example, okay, what I have to do? Well, I have to do, by, let's say, usual Hamiltonian analysis, is just the action, so it's just the Poisson bracket between the constraints acting on the fields. So this is just alpha. So this means, okay, if you calculate this expression, it happens the following. So this contains the momentum. I use the Poisson bracket, and the result is the following: is p slash kappa. Okay, so the variation of kappa alpha because of the constraint is just the p slash of kappa. Okay. So this is the variation of thetas. Now here, okay, I first give you the let's say the result, and then on Monday I will continue on this. So what is the variation of kappa of x mu? That will be again the Poisson bracket between kappa p slash theta acting on x mu. Sorry, this is D. Okay. So if you do the calculations, okay, I get what? Here I get kappa, so this is the p slash, this is just the momentum pi of alpha minus p slash theta acting on x mu. Okay, so I have two terms. One term is coming from here because I can have this contraction with this, which gives you kappa gamma mu pi alpha. Let me put the indices because otherwise alpha beta pi beta. And the other terms is coming from here. You get a 2 kappa. Okay, here there is a p slash give you p square kappa alpha theta alpha times what times p mu. So this is the kappa variation of x. This is not enough. This is yet not enough. Okay. Now I just leave you for exercise the following. You calculate what is the definition of pi mu, where pi mu is defined as I was saying before. So this is this expression here contains pi mu. So if I put this one here, this is pi mu. If you calculate pi mu, and you use the constraints, you use the definition that I gave you, that gives you minus kappa p slash gamma mu theta. Okay. Now, if you put all together, you can check that the reaction it is invariant on the following symmetry. So it is p slash kappa d of pi is equal to minus kappa p slash gamma mu theta, and d of kappa of E is equal to kappa, alpha d theta alpha d tau. On Monday, you can try in the weekend to calculate this, and you can check it, okay? And you can check that the action is invariant under the symmetry. So this is the gauge symmetry, because kappa is a local parameter. There is no gauge field associated to such a gauge symmetry. Okay, the action is invariant, and because of the symmetry, we get the SUSY matching, and the quantization on like cone. Okay, I think that we can stop here. As I said, you find these derivations in the chapter 5 of Green, Schwarz, and Witten. Okay. So next week I will start from this point. I will show you some other aspect of this. Then we move to strings. Okay, so we add the modes. Okay, then we construct the BRC charger for the bosonic strings for the Ramon-Schwarz, and then finally the last lectures I will construct the BRC charger for this model. Okay. So the covariant quantization of all these models, the bosonic models, the covariant quantization of Ramon-Schwarz, and then finally the covariant quantization of this model. Okay, thank you.